Today we're going to talk about multiplication and division of imaginary and complex numbers. Yesterday we learned about imaginary numbers and their purpose and use in Algebra 2. Just like I told you yesterday, the way imaginary numbers function, some of their properties are very similar to any other variable. And you're going to see this in numbers 1, 2, and 3. We need to multiply these binomials that include imaginary numbers. We're going to use a process called FOIL, which is basically just a double distribution. In order to do this multiplication, we're only going to look at one number in the first parentheses, and we're going to distribute that number to all the terms in the parentheses behind it. So I'm going to focus on 1. 1 times negative 2 is negative 2. 1 times positive 7i is positive 7i. When I'm done distributing the 1, I don't need that number anymore. Now I'm going to focus on the second term, 6i. I will distribute this term to both of the terms in the parentheses behind it. Positive 6i times negative 2 is negative 12i. Positive 6i times positive 7i is positive 42i squared. Yesterday, I taught you that there are 4 values of I. Let me write them down again. I, negative 1, negative I, 1. The main value that we're going to use today is I squared. We learned that I squared is equal to negative 1. So anytime we have an I raised to a power larger than 1, we do need to replace it with its value. So in this case, I'm going to take this positive 42 and I will multiply it times negative 1. Now, when I rewrite this so that I can see what can combine, I will rewrite it as a negative 42. Yesterday, I also told you that complex numbers are written with the real number first and the imaginary number second. So when we do our combination, let's look for the real numbers first. Negative 2 and negative 42 are real numbers. When I combine them, since they have the same sign, I'm going to add them and keep their sign. I get negative 44. Now I'm going to combine the imaginary parts. Positive 7i and negative 12i. Since they have opposite signs, I'm going to subtract them and keep the sign of the larger term. That will give me negative 5i. This is my final answer. Number 2 is also a double distribution problem, or a FOIL problem, but you don't see that second parentheses. Instead, you see this exponent, 2. Anytime you see a parentheses squared, it means that you have that parentheses 2 times. So I'm going to make the suggestion that you expand this problem so you can see those 2 parentheses, and then we'll work it the same way we did number 1. We're going to take the first term in the first parentheses and distribute it to each term in the second parentheses. When I do this, I'll get 4 and negative 8i. Now, I'm going to take the second term in the first parentheses and distribute it to both terms in the second parentheses. That will give me negative 8i and positive 16i squared. Now, just like I did in problem number 1, I'm going to replace I squared with its value, negative 1. That's going to cause my last term to become negative 16. You don't have to go through this process of rewriting. We can go ahead and combine the terms at this point. When I combine the real numbers, positive 4 and negative 16, I get negative 12. when I combine the imaginary terms, negative 8i and negative 8i, I get negative 16i. I'm going to leave number 3 for you to try on your own. The next concept that we're going to talk about is radicals that remain in the denominator. We talked about simplifying radicals in one of our previous lessons, but in that lesson, all the radicals either went away, they were perfect squares, or if we did have a radical remain, it remained in the numerator. You need to know that we are not allowed to keep a radical in the denominator. So, in these examples, I'm going to teach you a process called rationalizing the denominator. First, let's look at ways that we can simplify the problem. In number 4, I'm going to look at these outside numbers, 5 and 1. Do they have anything in common? Can I reduce them? No. Then I go to the inside numbers. Remember, these are called the radicands. Do these numbers have anything in common, or are they perfect squares? Well, they're not perfect squares, but they are both divisible by 3. So I'm going to do that. 3 divides into 3 one time. 3 divides into 21 7 times. Now my problem looks like this. The square root of 1 is a perfect square, and the answer is 1. So I can bring the answer out, and it will multiply with the coefficient in front of my radical. 5 times 1 is 5 over the square root of 7. So this is an example where, after my simplification, I still have this radical in the denominator. I can't have a radical in the denominator, so how do I get rid of it? What we will do is multiply it times the identical radical. It creates a perfect square. But I can't just add a radical into my problem because that throws off the balance of things. Algebra is all about keeping things balanced and equal. So whatever I do in one part of my fraction, I have to do the same exact thing in the other part of the fraction. So now I have 5 square root of 7 over the square root of 49. Well, the square root of 49 is a perfect square, and the answer is 7. This makes the radical go away in the denominator, and so now I have a final answer that is written in proper form. Number 5 and 6 are the same type of problem. I'm going to work number 5 and leave 6 for you to try on your own. In number 5, I don't have any coefficients, so I can't do any reduction there. 6 and 10, neither one of these are perfect squares, so I can't solve either one of them. But I can reduce them. Both of these numbers are divisible by 2. 6 divided by 2 is 3. 10 divided by 2 is 5. Even with this reduction, I'm still left with a radical in the denominator. So I'm going to use my process of rationalizing the denominator. I'm going to create that perfect square. If I multiply the denominator by the square root of 5, I have to multiply the numerator by the square root of 5 also, so that I can keep things balanced. Now I have the square root of 15 in the numerator and the square root of 25 in the denominator. The square root of 25 is a perfect square, and the answer is 5. The square root of 15 is in simplest form. I can't break it down and bring anything out, so I am done on this problem. Now, even though I have circled this, I do want to point out one thing, a common mistake people will make. Sometimes when you see this 15 and 5, you think maybe they can cancel. But remember, you can only cancel an outside number, a coefficient with a coefficient, and you can only cancel an inside or radicand with another radicand. You cannot mix the two. These last three problems all are examples of an I in the denominator. And you may say, why is that a problem? Well, yesterday I taught you that I is equal to the square root of -1. So if I can't have a radical in the denominator, I can't have an I in the denominator either. So just like in the previous problems, we want to simplify as much as we can, and then we're going to deal with, if there is an I in the denominator, I will use a process of rationalizing. In this first problem, I do have a negative in both the numerator and denominator, and I can cancel those. I also can cancel these numbers. 4 divides evenly into 8, leaving 2 in the numerator. So now I have 2 over I. Since I represents a radical, I can't leave it there. So the way that I rationalize I is to multiply it by itself. And whatever I do to the denominator, I do the same thing to the numerator. Now I have 2i over I squared. Well, I told you earlier in the lesson we were going to use this I squared a couple times. And here it is again. I squared is equal to -1. So I'm going to make that replacement. Now, you might think we're done, finally, but the truth is, there's one more thing you can't have in the denominator, and that's a negative number. So we know that when we divide anything by 1, we get the anything that we are dividing by. If we divide it by -1, it's just going to move the negative sign to the numerator. So I do want to write my final answer with the negative in the top and not in the denominator. Number 8 is the same type of problem. Start off by canceling your negatives. The numbers don't reduce, but I have this I. You can get rid of the I by multiplying denominator and numerator by I. I get 7i over 8i squared. Don't forget, replace I squared with -1. So now I have 7i over 8 times -1. So once I simplify it, it looks like this. But there's that other dilemma. I don't want to leave a negative in the denominator. So you can either push the negative to the numerator or you can bring it out front. You'll see it written both ways. I'm going to show you one more time just to make sure you got the hang of this. In this case, I cannot cancel the signs. I have a positive on top and a negative on the bottom. But I do need to get rid of this I. So I'm going to go ahead and do that. I have I over -9i squared. I'm going to make that replacement. I squared is the same as -1. Fortunately, when I multiply these two together, I get rid of the negative. So my final answer is I over 9.